Green sheets provided. Green sheets. Alright guys, so alright guys, so we have started talking about particulate suspension in the last class. Alright, my two timings are yet to be finalized with Shyam there. Alright, two timings are yet to be finalized. TAs are Sai, Prakhar and Amir. Hopefully you'll be using some Sai and Prakhar during the tutorials. Amir is at the back. Tutorial timings and menu I'll share with you over email. Alright guys, so reading that we have discussed in the last class. Here's the attendance policy. So attendance higher than 90% will be given plus 8%. Marks in the end, in the final score. Attendance between 75 to 90, 4%. 50 to 75, 0. And below 50, there will be 1 grade down. D grade में कुछ नहीं होगा, but in other cases there is going to be 1 grade down. Okay, no medical certificates will be considered. कोई medical condition के कारण if you have missed out one thing, that's fine. लेकिन अपना minimize करो, but those certificates won't be considered to make up for any your attendance. No late entry after 9-10 a.m. If you are entering, I will of course let you in, but attendance won't be provided. If a student with disability requires any reasonable accommodation for any of the components in the course, for lectures, for tutorials, anywhere, let me know and we can meet and discuss. Any questions, anyone? No? All good? Okay.
So this is 90% for class and only?
Just class, just lecture. Any questions? Anything, guys? For students entering after 9-10, I will request them to write their names here so that Ahmed can take a photo and make sure that in the attendance sheet, their attendances are not considered. Okay? Alright, so guys, last class we had started talking about particular suspension. So suspension by definition, it's at least a two-phase system, a continuous phase and a dispersed phase. And we discussed that will mostly stay in this region where the particles are not undergoing any grounding motion. Particles in this region also do have surface, do experience surface can experience strong surface interaction, but will mostly stay away from discussions on that. But wherever it's important, I'm going to point that out. Some examples of suspension that we discussed last class. The sugar molecules in dissolved or sugar cubes dissolved in water, which is sugar molecules are going to dissolve. We are not going to call that a suspension. For the purpose of this class, we are going to stay away from calling molecules particles, which in physics courses you might be calling. For the purpose of this class, molecules are molecules and particles are particles. Particles are typically much larger than size of molecules, and their sizes are much larger than mean free path. There are situations where particle size could be of the order of mean free path. For example, if so currently this air in this room is at 1 atmosphere. If we reduce the pressure here by large quantities, then mean free path could become larger and could be of the order of size of particles that we are dealing with. But in those situations, when those situations will arise, we'll know how to handle these continuum approximations that are laying the foundations of almost everything that we are studying in this course. Alright? So guys, I would strongly recommend you go over the attendance policies that I have shared today. I'll be sharing it on Google. So today I am giving exemptions to people entering after 9:10. Like next class se, I'll be asking them to write their names here, and in the end their names from the attendance list will be taken off. Amir is also counting the number of students who are here in each section, so proxy भी ज़्यादा नहीं चलेगी. If found somebody doing that, then disciplinary action will be taken. Okay, so motion of the single particle. In the last class we saw Stokes law. In vacuum, we assume, or when there is no fluid around the particle, the speed of the particle is not dependent on the particle size. But in Stokes law or flow inside a fluid, where drag force acting on the particle is going to be dependent on the size of the particle, the velocity of the particle is going to be dependent on the size of the particle. So larger size particles will have higher settling velocity, smaller size particles will have lower settling velocity. And we are going to do this experiment in the next CLP class, where we will be looking at settling velocity for rigid particles in a viscous. Alright, so for colloidal, we are typically going to stay away from studying colloidal suspensions in this class, but I'm just, in the last class we quickly went over what aspects are we missing out on. So, last class we discussed how mass transfer at a molecular scale, how mass transfer or heat transfer takes place. At the end of the day, it's purely random motion of these molecules that results in transfer of mass or transfer of constituents from high concentration to low concentration or high potential to low potential. Just the random motion is enough to ensure that. At the continuum scale, fixed law of diffusion describes it pretty well. Same goes for heat transfer. Heat transfer takes place from high temperature to low temperature, always and always. And here again, it's the random motion of these constituents, of these molecules, atoms forming these materials, which leads to transfer of heat from high temperature to low temperature. 100 years back, this, or about 120 years back now, Brownian, so all this is molecular, all these, I'm still not talking about the suspension or particles suspended in a fluid. About 100 years back, this idea of fluid made up by molecules was used by, or Bose theory was used by Einstein to estimate, to analytically derive how the Brownian diffusivity is going to look like for a particle, how Brownian diffusivity is going to look like for a particle. And he showed that Brownian diffusivity is going to go like kT by 6 pi mu r, where mu is the continuum viscosity of the fluid, K is Boltzmann constant, T is temperature, and R is size of the particle. And this is why are particles undergoing Brownian diffusion? क्या हो रहा है ये? I just want you guys to qualitatively understand क्या है Brownian diffusivity और क्या what is the origin of it. You were saying something.
So, particle are in continuous motion.
Particle क्यों है continuous motion में? जैसे मैं भी एक particle हूँ इस fluid में.
Because they have energy.
Because
They have
They have some energy.
kinetic energy between the particles and constant collision that takes a random path.
एक बार दोबारा से बोलना.
Due to the kinetic energy of the particles, it like collides with all the other particles and it has energy and it is random, completely random.
Yeah, so just like molecules, why are molecules moving around? I mean,
They are
oxygen molecules or nitrogen molecules here in the gas, they are moving around. Why are they moving around?
At each temperature, a molecule possesses half kT energy in each degree of freedom. So that's why.
They have thermal energy. They have an energy kT, as a result of which they are moving around. They are not moving in a uniform. I mean, if I throw this pencil with a velocity v, and if there was no air, this will continue to move with the velocity v, right? Here, in the case of molecules in the air or in the fluid, they are colliding with other molecules, as a result of which their directions changes. They are also exchanging momentum with other molecules. So this is a pure fluid motion, or molecules in a fluid motion. Now, if you have a particle in that fluid, that particle also has a thermal energy kT, right? I also have a thermal energy kT. मैं क्यों नहीं मूव कर रहा हूँ ऐसे?
Maybe the size matters.
Size matters.
Because in colloids, if the size is very small, that kind of disperse. They just move randomly throughout the fluid. That's the reason.
Yeah, I mean, there are other forces acting on me, and those forces, so for example, mg is acting on me with scales like my size, r cube. You can estimate mg with, you can compare mg with kT, and you can tell why you do not see me moving around. For the case of these particles, these are small entities. They have this thermal energy, and they are also exchanging momentum with these molecules around them. Except these molecules, the particle size is still large enough to assume that these the fluid around it is a continuum. Okay, exchange of this energy is leading to the random motion of the particle. This motion is called Brownian diffusivity. It is not molecular diffusivity. It's not the random motion of molecules that you are seeing here. It's not the same thing, which is also clear in the dependence of Brownian diffusivity on continuum property of the fluid, like viscosity, its size, its temperature. It's not dependent on इसका mass क्या है. It's not dependent on molecules की mean free path, the molecules in the fluid उनकी mean free path या उनका molecular weight क्या है. The molecular diffusion does depend on these things, and in couple of slides I'll show you that comparison. Okay, so Einstein used this, and of course Stokes' theory was used, the drag force acting on the particle 6 mu RV was used in this calculation, so it's called Stokes-Einstein diffusivity. This was Einstein's PhD work, and then Perrin, a French physicist, he took he used Einstein theory and did an experiment where, by looking at the concentration of the nanoparticle, I think micron size of 500 nanometer particles, by looking at the variation in concentration as a function of height, and you are going to do this calculation, at least the calculation in your tute. By looking at this, he estimated what Boltzmann constant is, and using Boltzmann constant, he estimated Avogadro number, which was one of the first estimates in literature for Avogadro number. एक और था इससे पहले, but yeah, after this discussion was sort of closed, or questioning of presence of molecules or atoms, that was closed. Both these guys, Perrin and Einstein, they shared their Nobel Prize in the 20s. Alright, so molecular diffusivity. And Brownian diffusivity, there is, as you can see, so molecular diffusivity of a molecule A in a fluid B. So here, these are the physical parameters on which that depends, whereas molecular diffusivity of a particle, this depends on these continuum properties of the fluid element. Alright. So another question, another problem in the tube sheet that you'll be handling, which will help you to understand how this Brownian motion, how distance traveled in the Brownian motion is going to look like. And in fact, this is not something specific to Brownian motion. Even molecular diffusivity, how your molecules are moving, that's going to be, it's again a random walk. So this kind of the question, the motion of the particle in the question is going to depict you the motion of, and it's really showing how almost any random motion is going to look like. If you close your eyes and start moving in a jungle, it's again going to be the same motion. After some time, you are going to lose sense of the direction and your motion is going to be random in nature. Same way here, so in the problem, I'm going to ask you to generate particles on a number line, place it at x equal to 0, and then each time step I'll ask you to generate a random number from 0 to 1, and let's say if the number is lies from 0 to 0.5, the particle takes a step forward. If the number lies between 0.5 to 1, the particle can step back. And I'm going to ask you to do this exercise for a long period of time, and by period or by time here, I essentially mean the number of steps that the particle is taking. 10 is for 3, 4, 5, 6, 7, 8 number of steps that your 1,000 or 10,000 or 100,000 particles will be taking. And I'll ask you to plot mean square displacement versus time for these particles. And the behavior, you are going to see two different kind of behaviors here. One for smaller times, let's say तुम सिर्फ 10 बार कर रहे हो, 10 steps ले रहे हो. One for larger times, 10 is for 7, 10 is for 8, 10 is for 9. And you guys may want to think about why there are these variations. This is, this kind of random walk is something very primitive to understanding stock markets at some level. All right, shall we? So we'll mostly be working length scales higher than a micron, where Brownian diffusivity is going to be negligible, and you can also tell from this relation that your Brownian diffusivity scales like 1 by r. जैसे जैसे बड़ी चीज होती जाएगी, Brownian diffusivity is going to go down. Alright, so although at these length scales also colloidal forces or interfacial forces could be important, but we'll mostly stay away from that. Alright, so let's start with so for example this creeping flow result that you guys have derived in your last semester fluid mechanics class, that is applicable, that is truly applicable only for particles which are not undergoing Brownian diffusivity or that are large enough that Brownian diffusivity is negligible. Although we'll see that incorporating Brownian diffusivity for your particles in the fluid It's not rocket science, and one can do that given that you are working in low Reynolds number fluid flow. Low Reynolds number flow पे let's jump on that. So anyone wants to go over क्या है low Reynolds number flow? Sorry? Creeping flow, low Reynolds number flow.
Very low velocity, very high viscosity,
Very low velocity,
and high viscosity.
high viscosity. So Reynolds number is rho dV by mu, where rho is density of fluid. Particle है fluid में, still it's density of the fluid. Navier-Stokes equation is written only and only for fluids. Okay, rigid particles के लिए नहीं है ये. Yeah, even for a deformable particle, which is a non-Newtonian fluid, उसके लिए नहीं है. Navier-Stokes equation is only and only for Newtonian fluids. Cauchy momentum balance equation one can write for non-Newtonian fluids, but let's not jump there. So he mentioned Stokes flow is low velocity flow, high viscosity flow. So rho dV by mu. If anything on the numerator is small, Reynolds number can be small. If anything in the denominator, and here it's only viscosity, that is high, again Reynolds number can be small. ठीक है, low Reynolds number, we have creeping flow or we have Stokes flow. These are synonyms, by the way. Low Reynolds number flow, creeping flow. What was the third thing? Stokes flow. I'll be using them. I'll be using all these terms, but they mean the same. ठीक है, low Reynolds number flow है. Now, what does that mean qualitatively?
Sir, the viscous forces are dominant. That's why the inertial forces they tend to become negligible. When inertia is negligible, all the temporal terms they starts becoming negligible. So any term and its values at time that can be neglected.
Agreed. Qualitatively, क्या difference है? The pen that I'm dropping in air, if this fluid was a very viscous fluid, तो क्या difference होगा इसमें?
It will not fall, it will stay there.
It will not
It will
follow
stay
a
there.
straight line.
Yes.
But
The moment we stop acting forces, it will stop right at the because there is no inertia, negligible inertia.
हाँ, so mg अगर लग रहा है तो mg है मान लो.
Okay, if mg is there, then the displacement will be lesser in creeping flow as compared to if it was inviscid.
More importantly, the qualitative difference would be this pen is undergoing acceleration as it's going down. Its velocity here is different from the velocity here, different from the velocity here. If it was a pure creeping flow, and if this pen was a spherical particle, non-spherical में थोड़ी और details आ जाती हैं. If this pen was a spherical particle, its velocity would be same here, here, and here. So it won't be undergoing any acceleration. Although an external force is acting on it, that force will be balanced by the drag force acting on the particle due to the fluid around it, ensuring that this particle is not undergoing any acceleration. So there is one major qualitative difference. The moment I turn on G, acceleration due to gravity, the particle will stop, as mentioned. Alright, so Navier-Stokes equation, you guys have seen this equation multiple times. What's the first term here on the left hand side?
Substantial derivative of velocity.
Yes, and so you can think of first term as acceleration term or rate of change of velocity. The second term is u dot del u.
Viscous term.
नहीं, पहली term left hand side, second term on the left hand side. U dot del V. Convection term, we call it, or advection term. And I mean, guys, I would like you to remember, I mean, this equation along with mass transfer equation and heat transfer equation, these are like three brothers or sisters, and in mass transfer or heat transfer, you have the second term will be U dot del T. In heat transfer, in mass transfer, it will be U dot del C. Convective terms for mass transfer, convective terms for heat transfer. Here, it's for momentum transfer. Okay? In this entire equation, this is the only term that is non-linear. U dot del U. यहाँ U square वाली dependence आ रही है, which is not the case for anything on the right hand side. And in your mass transfer and heat transfer equations also, it's this convective term which needs to be solved using Navier-Stokes equation. मतलब velocity को solve करना है fluid में. What is the difference between Navier-Stokes equation and Bernoulli's equation? Anyone?
Bernoulli's is for irrotational form.
हाँ यार फिजिकली मुझे इतने कॉम्प्लिकेटेड टर्म्स मत बोला करो, फिजिकली मुझे कुछ बताओ जो इजी है.
It's a non-viscous.
Non-viscous liquids, you can write Bernoulli's equation. Here your viscosity is, in fact one can derive Bernoulli's equation using Navier-Stokes equation by neglecting the viscous numbers. So, by the way, this is a question I'm going to ask you guys. I'm telling you beforehand. cll332 Viva question: difference between Bernoulli equation and Navier-Stokes equation. Somebody can record it, and in the Vivas, people will fail to answer this question. Alright, so the unknowns in this equation is velocity and pressure. And since it's only one equation and there are two variables, one needs two equations to solve for two variables, and the second equation is continuity equation. If your fluid is incompressible, the continuity equation looks like this: divergence of u equal to 0. Alright, so again, in the Navier-Stokes equation, the left hand side is non-linear, the right hand side is linear in terms of velocity, this unknown variable. Now, when I'm working at low Reynolds number flow, आज के लिए नहीं है attendance policy. So when I'm working at low Reynolds number flow, one can neglect the left hand side. Okay, one can neglect these non-linear terms. And the moment I'm only left with these linear terms, you'll see that there are a lot of qualitative changes that is going to happen. And understanding them, some of these things you will not, I mean, in general, you think that we encountered particles in fluid at finite or high Reynolds number in our day-to-day life. So some of the qualitative features of low Reynolds number fluid, they will not be obvious to you. So, I'm just low Reynolds number, high Reynolds number, or inviscid fluid where viscosity, we are neglecting the viscosity term. some examples of low Reynolds number flow. So in general, we call low Reynolds number flow as a flow with low velocity, but that is not necessarily always true. When I'm working with,
Very big viscous.
so for example, when I'm working with small size particles, so these are red blood cells flowing in a fluid. So velocity could be few centimeter per second, but if the size is small enough, a micron or so, my Reynolds number could still be small. And there I'm talking about movement of glaciers, huge entities, but the speeds are very, very small. Here I'm talking about flow inside our flow below the Earth crust. Or inside Earth's mantle. Here the viscosities are very high. Viscosity of the fluid is very high, and the natural convection that is taking place here is again a low Reynolds number. One thing to note here is, while we'll be talking about particles suspended in a fluid, Stokes flow is not, Stokes flow equation is not, or Stokes equation is not for the particle phase. Or Navier-Stokes equation is not for the particle phase. Okay, so this is only Stokes equation or continuity equation or implicit fluid equation. It's only and only for the continuous phase. It's only and only for the fluid phase. For the particle phase, I mean, if it's a rigid particle, then Newton's equations will be valid. Ma is equal to summation of forces acting on the particle. Okay, guys, can you please stop talking? If you have any questions, please, you can ask me. So let's look at some of the consequences of Stokes flow or viscous flow. Since we don't have del V by del T term or V dot del V term, we know from there, since velocity is no longer a function of time, so instantaneity is going to be there. The moment I'm dropping this pen, we stop writing, thinking that I'll be using this pen to avoid. So the moment I'm dropping this pen, the velocity is going to be constant in a viscous flow. Okay, linearity is also there, and reversibility. Any example that you guys can think of? Where the linearity of this equation so instantaneous del V by del T is 0, so no acceleration is there. Velocity can still, by the way, while here the velocity is constant, the moment I'm dropping, it could still be a function of time in the sense, let's say, I can tune acceleration due to gravity. I can tune mg acting on the particle as a function of time. Let's say g is undergoing a sinusoidal motion. It's 0 at t equal to 0, then at t equal to, after some time it's 1, it's again 0 or minus 1. The velocity of this particle is going to be in sync with the mg acting on it. It can go up and down, so it could be changing because of this factor, but there's no acceleration. It's instantaneously reaching its terminal velocity. And in the next class, I'm going to question that instantaneity too, but for the time being, note that del V by del theta 0 being negligible means the particle is going to reach instantaneous, it is going to reach its terminal velocity instantaneously. And this is something that we have used in the in our discussion on drag force acting on the particle and the resulting thermal velocity. In fact, I'm questioning that instantaneity now. So now I'm asking, let's say I'm dropping this pen, or assume this pen to be a spherical particle for the time being. I'm dropping at t equal to 0. This is definitely zero velocity. I'm holding it at zero velocity. And then I'm saying that it's reaching its terminal velocity instantaneously. Now, you can ask how much time is it taking to go from 0 to whatever the terminal velocity is. Or what do we mean by instantaneous movement from 0 velocity to terminal velocity? What kind of guys, please leave if you want to talk with anyone in the class. तो दोनों जा सकते हैं बाहर. So what time are we? How fast is this instantaneous motion? Another thing to note here is we can say Reynolds number is Stokes law is present when Reynolds number is much smaller than 1. But what is low velocity? Guys, in future I may ask you to tell me your name if I find you talking in the class. And sometimes I remember names, and when I'm correcting answer sheets, if those names pop up, so what is this is important, guys. So he when I asked when is low Reynolds number present, he said that when velocities are small. What do we mean by small velocities? What is the small velocity? How small velocity can I call small? How small? What magnitude of velocity can I call small? Please, some response will help here.
Millimeter per second.
Yeah, I mean 1 millimeter per second. How about
Of the order of 1 by density of that particular fluid.
of the order of 1 by density? Yeah, density की of units, 1 by density की units are different from velocity
Of the
units.
order of that.
Mu upon
RD.
RD.
Mu upon
It
RD.
should be much less than mu upon RD.
R is
R is the radius and the meter density rho and R radius.
okay. D is your density, not okay. ठीक है. हाँ मतलब तुम बस velocity को एक जगह रख रहे हो. Yeah. So I mean I want you guys to stay away from calling a dimensional quantity as small or large.
Then we don't have a reference.
Nothing is small, nothing is large without comparing. It's only comparison. I mean, non-dimensional quantities can be large or small. When I'm writing Reynolds number much less than 1, that means it's a small quantity. And guys, I'm not telling you at what Reynolds number creeping flow is going to be. I'm not giving a number here. I'm not saying at Reynolds number 0.1 or at Reynolds number 0.01 or at Reynolds number 10 is for -3 or 10 is for -20, your creeping flow is going to be present. Mathematically speaking, I'm only and only saying Reynolds number much less than 1, where Stokes law or creeping flow is going to be present, or this equation is going to be valid. No, for the purpose of this class, no dimensional quantity should be called large or small. 1 millimeter per second may look like a very small velocity, but for example, for this gum in my teeth, which is moving at velocity much smaller than that, this velocity is pretty high. So dimensional quantities can be called large and small when compared with any other same dimension quantity. So when I'm saying KT is small, for me, it has to be compared with some other quantity with the same dimension. So gravitational force acting on me has to be compared with thermal energy for me to say that thermal energy is large for me or small for me, for my motion. Okay, so let's make that point that we will not use small or large terms for dimensional quantities. If I'm using it, please point that out and ask me with what quantity are you comparing. Okay? Any questions here? Alright, so now when I'm saying instantaneously, one question could be, how instantaneous is this instantaneous? Since we are talking about time, a quantity with dimensions of time, with what other time am I comparing this time? अगर ये 1 घंटे में टर्मिनल वेलोसिटी को अचीव कर रहा है, that time is much smaller than time it's taking a particle to move from here to Antarctica, or a gas molecule to move from here to Antarctica. Again, comparison of time, this time 1 hour could be a very small time compared to some time scales, but it could be much larger than the time that
We can compare it with when the particle is moving in low viscous fluid.
sorry?
We can compare it with the time it takes in low viscous fluid.
Again, how do you define a time associated with a motion of a particle in low viscous fluid?
We can assume it that way.
Anyway, so how small is this small? When I'm calling it instantaneous, how small is it? And under what situation or at what time scale do I need to worry about the time it's taking this particle to reach terminal velocity in Stokes law, which I'm calling instantaneous. So let me now non-dimensionalize my Navier-Stokes equation in a different form. So earlier when we were non-dimensionalizing it, I was non-dimensionalizing time with L by D, where L is L by V, sorry, where L is my the particle size or whatever my length scale associated with the flow is, and UC is again my velocity associated with the flow. I was doing that. Now, instead of writing time as writing time as L by U, or using L by U to non-dimensionalize my time, जो इस वाली क्वेश्चन में हमने किया, I'm non-dimensionalizing my time using critical time tau c, and LC and UC are the same. So now I'm non-dimensionalizing t as t dash is equal to t by tau c, and I don't know what that time scale is. As a result, this entire equation now when non-dimensionalized gives me another non-dimensional number called Strahul number, where Strahul number is LC by UC times tau c. Earlier, I just assumed that tau c is equal to LC by UC, so Strahul number 1 करके उसे भूल गए थे. Okay. Now for me, sorry.
What is LC?
LC is the length scale associated with the fluid. UC is the velocity scale associated with the fluid. यहाँ पे जो U और L है वो LC UC है. Okay, now for me to say that this is a Stokes flow or this is a low Reynolds number flow, this equation has to be again negligible, and for that, for this Reynolds number much smaller than 1 means this term is negligible, but Reynolds number times Strahul number could still be order 1. For this to be negligible, my Reynolds number times Strahul number has to be much less than 1. Let's see. Now I know that Reynolds number is much less than 1, that is given to me. For in situation where Reynolds number times Strahul number is order 1, क्या होगा? In that case, Strahul number has to be much larger than 1 for this product to be of the order 1. And for that to happen, this non-dimensional number has to be much larger than 1, means my tau c has to be much smaller than my LC by UC. Physically इसका क्या मतलब है? Am I saying now कि your fluid is the motion your particle is not going to reach terminal velocity instantaneously? What is LC by UC for motion of this spherical particle falling with the its terminal velocity? In this kind of problem, I can think of a length scale associated with the size of the particle as LC. So, जो भी size है particle का, that is my LC, and whatever the terminal velocity is, that is UC. So, I am going to reach terminal velocity at time scales of the order of LC by UC. For time scales much smaller than 1, there is acceleration is going to be present. So time जितना लग रहा है इस particle को to move a distance equal to its own size. L by U क्या है? Time it's taking to move a distance to move a distance equal to its own size. So when that kind of time is involved, it's Stokes flow.
So can you please repeat?
When L by U is time it's going to take to cover a distance equal to its own size.
Oh, with the velocity of terminal velocity.
With its terminal velocity. मतलब वही velocity है जो पता है इस दुनिया में. I mean, in this world there is no other length scale, there is no other time scale or velocity scale. So L by U is the time that it's going to take to travel a distance equal to its own size. So when my time is going to be of that order, my Strahul number is going to be order 1. And in that case, Reynolds number times Strahul number is still going to be much smaller than 1. So Stokes equation valid है that.
Okay.
However, when I'm at time scale is much smaller than the time it's taking the particle to cover its own distance, my Reynolds number times Tropple number could be finite, as a result of which du by dt could still be important.
So what is the tau c we are mentioning here?
Tau c मुझे नहीं पता. Tau c is the time over which मैं ये equation को देख रहा हूँ, motion को
देख रहे
देख रहा हूँ. हाँ.
ऐसे रहता
Time is that variable.
Okay.
I'm just saying that when the time is, when I'm in this regime of times of the order of time it takes for the particle to cover its own size, then we are safe. Reynolds number equation is valid. Del u by del t is 0. If I'm looking at very small times, and the moment I'm saying very small time, which is a dimensional quantity, you should be asking me kitna small hai. And that very small time is compared to the time that the particle is taking to cover distance equal to its own size. Am I making sense, guys?
Yes.
उधर से आवाज नहीं आ रही.
Yes.
Am I making sense, ma'am?